It is part 2 of section 2.4, big O and little o notation. A sequence alpha n is said to be in big O of beta n if there is a positive number k such that this inequality is satisfied for large n. Equivalently, the alpha n over beta n in modulus is bounded by k. In this case, we say alpha n is in big O of beta n, and we are using here the notation alpha n in big O of beta n, or we are using equality sign alpha n equals big O of beta n. A sequence alpha n is said to be in little o of beta n if there is a sequence epsilon n converging to 0 such that this inequality is satisfied for large n. That is same as this the limit of alpha n over beta n is 0. So that here now alpha n is basically here now if beta n is increasing, then here alpha n is slower. So that anyway this is similar than that, but in this case, and as n becomes larger and larger and is bounded by some number, means that the same order basically if it goes to infinity, then is bounded by k times of the increasing speed, so that once they are both increasing, then and more or less the same order, but in this case the alpha n is slower. Okay. Anyway, in this case we say alpha n is in little o of beta n, and we are using the notation alpha n is in little o of beta n, or same we may use equality sign alpha n equals little o of beta n. Let's see examples. Show that this one and that one. Let's try to show this second part. That means that here f of n is big O of n to the minus 2 and simultaneously little o of n to the minus 1. So that we'll try to show two parts for this one. That is the first part, and that is now second part. Okay, for first part, now fn over that one, so that fn over now n to the minus 2. Okay, that one is same as n plus 3 divided by n cubed plus 20 n squared and divided by n to the minus 2. So that is same as now n squared will be multiplied over there, so that n cubed plus 3 n squared over n cubed plus 20 n squared, right? Okay, this is cubic and cubic, so that here divided by n cubed we have 1 plus and 3 over n divided by 1 plus 20 over n. As n approaches infinity, these two terms will approach 0, so that eventually this ratio will converge to 1 as n increases. So here we didn't use absolute sign, but anyway, as n approaches infinity, these quantities are positive, so that without absolute sign, here we have that, but with the absolute sign, we'll have the same result. So it is, you can say that right now this is less than 1. In fact, it's converging to 1 from below, so it's always bounded by 1. So it is playing the role of k. So the ratio is bounded by 1, which is k, so that we can say this portion f is in big O of n to the minus 2. Okay. How about the second part? Okay, here. Now we have to check the ratio fn over n to the minus 1, or fn divided by n to the minus 1. Okay, then here, rather than n to the minus 2, we put here n to the minus 1. Then n will be multiplied on the top, so that there will be n squared plus 3n divided by here n cubed, the same bottom here, plus 20 n squared. Now this is cubic on the bottom, and the numerator is quadratic, so that bottom increases much faster than this one. So we know that that will convert to 0 as n approaches infinity. So here, now that is satisfying this one, alpha n over beta n, limit is 0. As n increases and approaches infinity, we can see that the ratio, absolute value, is approaching 0. So that means that f of n is in little o of n to the minus 1. Okay? So we prove that. Okay. For the other one, you may check it yourself. Now we define the little big O and little o for the quantities sequence converging to 0. Suppose g of h is converging to 0 as h approaches 0. A quantity f of h is said to be in big O of gh if there is a positive number k such that f over g in modulus is bounded by k for h sufficiently small. That means that as h approaches 0. In this case, we say that f of h is in big O of g over h, and we are using this notation, or sometimes again the equal sign. Little o of gh can be defined the same way as for the sequences, and in fact the ratio converges to 0 as h approaches 0. Then we say that capital F of h is in little o of g over h. Let's see this example. Taylor's series expansion for cosine x is given as here. Cosine x as now, this is even function, so in polynomial, here you can see only even with the terms, so we can write in this way. But if you're using computer algebra software, and if you try to get Taylor expansion for cosine x and about 0 and 4 terms, then you'll see this one. Now, in fact, and linear term is 1 term, but the coefficient is 0, so that we don't have here. And also third term with coefficient 0, so that constant term, first term, second term, third term, these 4 will make 4 terms. So the 4 term expansion is only this one, and then that is the remainder, order x to the 4. You'll see such output. Now, this means that this remainder portion is now a big O of x to the 4. Now, we'll check why it is given in this way, why it is in big O of x to the 4. Okay. If we define this portion as capital F of x and divide by x to the 4, then here we can reach this term divided by x to the 4, divided by x to the 4, so that here we have these terms. Now, this summation, this is alternating series and becoming smaller, smaller, smaller. Also, x is approaching 0, so that later terms are much smaller. In this case, this summation is bounded by the first term, which is 1 over 24. So this whole term for small x is bounded by 1 over 24. So the ratio in modulus is bounded by a number k, which is 1 over 24, so that we can say f is in order big O of x to the 4. So the computer output is given in this way. Choose the correct assertions in each. N is approaching infinity. Okay. Now, let's check if the first assertion is correct. Okay. To check it, we have to check the ratio. Okay. N squared plus 1 over n cubed over, this is alpha n, this beta n, 1 over n, right? So it can be written in this way. That is now n cubed plus n divided by here n cubed, right? Okay. This one is converging to 1 and 4, but it's slightly larger than 1, and for every n it is bounded by 2, but anyway it is converging to 1. So we can say that this term is in big O of 1 over n, but it is saying little o, so that is wrong. For that one, okay, this term divided by 1, that is the same as this term. Now, as n approaches infinity, that is blowing up. So it is becoming larger and larger, so that it cannot be here little o of 1. In fact, also it cannot be big O of 1. But for that one, if you change this on big O, then it's true. It's correct. But for that one, it's wrong. Same way, you can check that. And now let's go to fourth one, this one. Okay, that is, we start with the ratio 1 over n log n divided by 1 over n. Then we cancel 1 over n, and then here there is 1 over log n remainder. Now as n approaches infinity, this one approaching 0, so that here this term is in little o of that term, right? So the correct assertion is only this one. F of h is defined in this way. What are the limit and the rate of convergence of f of h? Okay, let's try to find the limit in the beginning, and then we'll try to find the rate of convergence. Okay. Now in part 1, okay, limit as h approaches 0, we can find it. So it's the limit here, h approaches 0, f of h, that is same as the same limit, and here 1 plus h minus e to the h over h, right? Okay. Now, as h approaches 0, the top is approaching 0, and bottom also approaching 0. So this problem requires a little bit of knowledge from calculus. And 0 over 0 shape, then you can use L'Hopital's rule so that the limit is the same as now the limit of ratio from each one. Here you can get derivatives. Derivative of this one is same as 1 minus e to the h and over, and that is 1. So if you don't have background from calculus, then in chapter 3 we'll deal with the calculus, so that by then you may not understand it. However, later after finishing chapter 3, if you come back here, then you can see it quite easily. Okay. Now, if h approaches 0, then here top approaches 0 and bottom is 1, so that is 0. So that limit is 0. That means that f of h is approaching 0. Now here, secondly, we want to find the rate of convergence of f of h. That means that we have to find here k such that f of h is in big O of h to the k. So we have to find this k. So the problem is asking to find the rate of convergence of f of h. That means that here we have to find k such that f of h is in big O of h to the k. Okay. Now to find the k exactly, we start with the definition, the ratio f of h. Now f of h divided by h to the k. Okay, that is same as here 1 plus h and minus e to the h, and there is a 1h originally, and then h to k, so that h k plus 1. Now k is non-negative number, so that once h approaches 0, then here top is approaching 0 and bottom approaches 0. So that once you apply limit, then the limit will be the same as the ratio of their derivatives. So that derivative of this top is 1 minus e to the h, and derivative of bottom is now k plus 1 will go out, and h to the k here. Okay. Now for that one, once h approaches 0, then top approaches 0, and here, and to get so we have to find the k as large as possible. So once it is approaching 0, then we can make bottom approaches 0. So that means that once k is integer, then k doesn't have to be 0. In fact, k can be larger than equal to 1, so that bottom goes to 0. Okay, so 0 over 0 in limit, so that again we may make a derivative. Then top is e to the minus e to the h divided by, now that is here k plus 1, the constant, and k comes out, and h to the k minus 1. Now top is approaching -1, and so that now it cannot approach 0, so it must be a positive number and non-zero. In order to do that, here if k is for example 2, then h is 1, h is approaching so that the value will blow up. So k cannot be 2. And so we decide at this moment here k is 1, then we know that here 0, okay, 1, so that is 1, so that -1 over 1 times here bottom and 1 plus 2, so that is approaching -1 over 2, okay? So that k cannot be 2. Once 2, then it's approaching 0, so the quantity blowing up, so we cannot say that. So here k is 1, so f of h is big O of h, okay? It's a little bit complicated, but you can understand this one later on after learning calculus, okay? Show that these assertions are not true if you have calculus background, and by using the definition, this term divided by x squared and this term divided by that one, and the exact same way, you can check that these all are not true, okay? It's false. You can check it yourself. Okay, that's the end of the section. Thank you.